In geometry, curvilinear coordinates are a coordinate system for Euclidean space in which the coordinate lines may be curved. These coordinates may be derived from a set of Cartesian coordinates by using a transformation that is locally invertible, a one-to-one map at each point. This means that one can convert a point given in a Cartesian coordinate system to its curvilinear coordinates and back. The name curvilinear coordinates, coined by the French mathematician Lamé, derives from the fact that the coordinate surfaces of the curvilinear systems are curved. Well-known examples of curvilinear coordinate systems in three-dimensional Euclidean space are three: a Cartesian, cylindrical and spherical polar coordinates. A Cartesian coordinate surface in this space is a coordinate plane. For example, z equals 0 defines the xy plane. In the same space, the coordinate surface r equals 1 in spherical polar coordinates is the surface of a unit sphere, which is curved. The formalism of curvilinear coordinates provides a unified and general description of the standard coordinate systems. Curvilinear coordinates are often used to define the location or distribution of physical quantities which may be, for example, scalars, vectors, or tensors. Mathematical expressions involving these quantities in vector calculus and tensor analysis, such as the gradient, divergence, curl, and Laplacian, can be transformed from one coordinate system to another. According to transformation rules for scalars, vectors, and tensors, such expressions then become valid for any curvilinear coordinate system. Depending on the application, a curvilinear coordinate system may be simpler to use than the Cartesian coordinate system. For instance, a physical problem with spherical symmetry defined in R3. For example, motion of particles under the influence of central forces is usually easier to solve in spherical polar coordinates than in Cartesian coordinates. Equations with boundary conditions that follow coordinate surfaces for a particular curvilinear coordinate system may be easier to solve in that system. One would for instance describe the motion of a particle in a rectangular box in Cartesian coordinates, whereas one would prefer spherical coordinates for a particle in a sphere. Spherical coordinates are one of the most used curvilinear coordinate systems in such fields as earth sciences, cartography, and physics, in particular quantum mechanics, relativity, and engineering. Orthogonal curvilinear coordinates in three dimensions, coordinates, bases, and vectors. For now, consider 3D space. A point P in 3D space, or its position vector r, can be defined using Cartesian coordinates x, y, z, equivalently written x1, x2, x3, by r equals x, e, x, plus y, e, y, plus z, e, z. Display style mathbf r equals x mathbf e underscore x plus I mathbf e underscore y plus z mathbf e underscore z, where x, a, e, z are the standard basis vectors. It can also be defined by its curvilinear coordinates q1, q2, q3. If this triplet of numbers defines a single point in an unambiguous way, the relation between the coordinates is then given by the invertible transformation functions x equals f1 q1 q2 q3, y equals f2 q1 q2 q3, z equals f3 q1 q2 q3. Display style x equals f caret 1 q caret 1 q caret 2 q caret 3 backslash y equals f caret 2 q caret 1, q caret 2, q caret 3, backslash z equals f caret 3, q caret 1, q caret 2, q caret 3, closing curly bracket, q1 equals g1 x y z, q2 equals g2 x y z, q3 equals g3 x y z. Display style q caret 1 equals g caret 1 x y z, backslash q caret 2 equals g caret 2 x y z, backslash q caret 3 equals g caret 3 x y z, closing curly bracket. The surfaces q1 equals constant, q2 equals constant, q3 equals constant are called the coordinate surfaces, and the space curves formed by their intersection in pairs are called the coordinate curves. The coordinate axes are determined by the tangents to the coordinate curves at the intersection of three surfaces. They are not in general fixed directions in space, which happens to be the case for simple Cartesian coordinates, and thus there is generally no natural global basis for curvilinear coordinates. In the Cartesian system, the standard basis vectors can be derived from the derivative of the location of point P with respect to the local coordinate E x equals r x, E y equals r y, E z equals r z. Display style mathbf E underscore x equals dfrac partial mathbf r partial x backslash mathbf E underscore y equals dfrac partial mathbf r partial y backslash mathbf E underscore z equals dfrac partial mathbf r partial z, closing curly bracket. Applying the same derivatives to the curvilinear system locally at point P defines the natural basis vectors. H1 equals r q1, H2 equals r q2, H3 equals r q3. Display style mathbf H underscore 1 equals dfrac partial mathbf r partial q underscore 1 backslash mathbf H underscore 2 equals dfrac partial mathbf r partial q underscore 2 backslash mathbf H underscore 3 equals dfrac partial mathbf r partial q underscore 3, closing curly bracket. Such a basis, whose vectors change their direction and/or magnitude from point to point, is called a local basis. All bases associated with curvilinear coordinates are necessarily local. Basis vectors that are the same at all points are global bases, and can be associated only with linear or affine coordinate systems. Note: for this article E is reserved for the standard basis, Cartesian, and HB is for the curvilinear basis. These may not have unit length, and may also not be orthogonal. In the case that they are orthogonal at all points where the derivatives are well defined, we define the Lamé coefficients after Gabriel Lamé by H1 equals pipe H1 pipe H2 equals pipe H2 pipe H3 equals pipe H3 pipe. Display style H underscore 1 equals mathbf H underscore 1 backslash H underscore 2 equals mathbf H underscore 2 backslash H underscore 3 equals mathbf H underscore 3 and the curvilinear orthonormal basis vectors by B1 equals H1, H1, B2 equals H2, H2, B3 equals H3, H3. Display style mathbf b_1 equals dfrac mathbf h_1 h_1 backslash mathbf b_2 equals dfrac mathbf h_2 h_2 backslash mathbf b_3 equals dfrac mathbf h_3 h_3 closing curly bracket. It is important to note that these basis vectors may well depend upon the position of P. It is therefore necessary that they are not assumed to be constant over a region. They technically form a basis for the tangent bundle of R3. Display style mathbar R3 at P, and so are local to P. In general, curvilinear coordinates allow the natural basis vectors high not all mutually perpendicular to each other, and not required to be of unit length. They can be of arbitrary magnitude and direction. The use of an orthogonal basis makes vector manipulations simpler than for non-orthogonal. However, some areas of physics and engineering, particularly fluid mechanics and continuum mechanics, require non-orthogonal bases to describe deformations and fluid transport to account for complicated directional dependencies of physical quantities. A discussion of the general case appears later on this page. Vector calculus. Differential elements in orthogonal curvilinear coordinates. Since the total differential change in is d r equals r q 1 d q 1 plus r q 2 d q 2 plus r q 3 d q 3 equals h 1 d q 1 b 1 plus h 2 d q 2 b 2 plus h 3 d q 3 b 3. Display style d math bf r equals dfrac partial math bf r partial q caret 1 dq caret 1 plus dfrac partial math bf r partial q caret 2 dq caret 2 plus dfrac partial math bf r partial q caret 3 dq caret 3 equals h underscore 1 dq caret 1 math bf b caret 1 plus h underscore 2 dq caret 2 math bf b caret 2 plus h underscore 3 dq caret 3 math bf b caret 3. So scale factors are h I equals pipe r q I pipe. Display style h underscore I equals left frac partial math bf r partial q underscore I right. In non-orthogonal coordinates, the length of d r equals d q 1 h 1 plus d q 2 h 2 plus d q 3 h 3. Display style d math bf r equals dq caret 1 math bf h caret 1 plus dq caret 2 math bf h caret 2 plus dq caret 3 math bf h caret 3 is the positive square root of d r equals d q I d q j h I h j. display style d math BF r c dot d math BF r equals dq caret I dq caret j math BF h underscore I c dot math BF h underscore j. With Einstein summation convention, the six independent scalar products Gij equals high Hj of the natural basis vectors generalize the three scale factors defined above for orthogonal coordinates. The 9 Gij are the components of the metric tensor, which has only three non-zero components in orthogonal coordinates. G11 equals h1 h1. G22 equals h2 h2. G33 equals h3 h3. Covariant and contravariant bases, spatial gradients, distances, time derivatives and scale factors are interrelated within a coordinate system by two groups of basis vectors. Consequently, a general curvilinear coordinate system has two sets of basis vectors for every point. B1, B2, B3 is the covariant basis, and B1, B2, B3 is the contravariant. A, K, A. Reciprocal bases. The covariant and contravariant basis vectors types have identical direction for orthogonal curvilinear coordinate systems, but as usual have inverted units with respect to each other. Note the following important equality. B, I, B, J equals delta J, I. Display style math BFB caret I c dot math BFB underscore J equals delta underscore J caret I, wherein delta J I display style delta underscore J caret I denotes the generalized Kronecker delta. A vector V can be specified in terms either basis I, E, V equals V1, B1, plus V2, B2, plus V3, B3, equals V1, B1, plus V2, B2, plus V3, B3. Display style math BF V equals V caret 1 math BFB underscore 1 plus V caret 2 math BFB underscore 2 plus V caret 3 math BFB underscore 3 equals V underscore 1 math BFB caret 1 plus V underscore 2 math BFB caret 2 plus V underscore 3 math BFB caret 3. Using the Einstein summation convention, the basis vectors relate to the components by V, B, I equals V, K, B, K, B, I equals V, K, delta, K, I equals V, I. Display style math BF V C dot math BFB caret I equals V caret K math BFB underscore K C dot math BFB caret I equals V caret K delta underscore K caret I equals V caret I. V, B, I equals V, K, B, K, B, I equals V, K, delta, I, K equals V, I. Display style math BF V C dot math BFB underscore I equals V underscore K math BFB caret K C dot math BFB underscore I equals V underscore K delta underscore I caret K equals V underscore I and V B I equals V K B K B I equals G K I V K display style mathbf v c dot mathbf b underscore I equals v caret k mathbf b underscore k c dot mathbf b underscore I equals g underscore key v caret k v b I equals v k b k b I equals g k I v k display style mathbf v c dot mathbf b caret I equals v underscore k mathbf b caret k c dot mathbf b caret I equals g caret key v underscore k, where g is the metric tensor. See below. A vector can be specified with covariant coordinates, lowered indices, written vk, or contravariant coordinates, raised indices, written vk. From the above vector sums, it can be seen that contravariant coordinates are associated with covariant basis vectors, and covariant coordinates are associated with contravariant basis vectors. A key feature of the representation of vectors in tensors in terms of indexed components and bases vectors is invariance, in the sense that vector components which transform in a covariant manner, or contravariant manner, are paired with basis vectors that transform in a contravariant manner, or covariant manner. Covariant basis. Constructing a covariant basis in one dimension. Consider the one-dimensional curve shown in Fig. 3. At point P, taken as an origin, x is one of the Cartesian coordinates, and q1 is one of the curvilinear coordinates. The local, non-unit, basis vector is b1, notated h1 above, with b reserved for unit vectors, and it is built on the q1 axis, which is a tangent to that coordinate line at the point P. The axis q1 and thus the vector b1 form an angle alpha with the Cartesian x-axis and the Cartesian basis vector e1. It can be seen from triangle PAB that cos alpha equals pipe e1 pipe b1 pipe e1 pipe equals pipe b1 pipe cos alpha. Display style cos alpha equals CFRAC mathbf e underscore 1 mathbf b underscore 1 quad right arrow quad mathbf e underscore 1 equals mathbf b underscore 1 cos alpha, where e1 b1 are the magnitudes of the two basis vectors i.e. the scalar intercepts PB and PA. Note that PA is also the projection of B1 on the x-axis. However, this method for basis vector transformations using directional cosines is inapplicable to curvilinear coordinates for the following reasons. By increasing the distance from P, the angle between the curved line Q1 and Cartesian axis x increasingly deviates from alpha. At the distance PB, the true angle is that which the tangent at point C forms with the x-axis, and the latter angle is clearly different from alpha. The angles that the Q1 line and that axis form with the x-axis become closer in value the closer one moves towards point P and become exactly equal at P. Let point E be located very close to P, so close that the distance P is infinitesimally small. Then P measured on the Q1 axis almost coincides with P measured on the Q1 line. At the same time, the ratio PD being the projection of P on the x-axis, becomes almost exactly equal to cos alpha. Let the infinitesimally small intercepts PD and P be labeled, respectively, as dx and dq1. Then, cos alpha equals d x dq1 equals pipe e1 pipe b1 pipe. display style cos alpha equals CFRAC dx dq caret 1 equals frac math BF E underscore 1 math BF B underscore 1. Thus, the directional cosines can be substituted in transformations with the more exact ratios between infinitesimally small coordinate intercepts. It follows that the component projection of B1 on the x-axis is P1 equals B1 E1 pipe E1 pipe equals pipe B1 pipe E1 pipe E1 pipe cos alpha equals pipe B1 pipe dx dq 1 P1 pipe B1 pipe equals dx dq 1. Display style P caret 1 equals math BFB underscore 1 CDOT CFRAC math BF E underscore 1 math BF E underscore 1 equals math BFB underscore 1 CFRAC math BF E underscore 1 math BF E underscore 1 cos alpha equals math BF B underscore 1 CFRAC dx dq caret 1 quad right arrow quad CFRAC P caret 1 math BFB underscore 1 equals CFRAC dx dq caret 1. If chi equals chi x1 x2 x3 and chi equals chi q1 q2 q3 are smooth, continuously differentiable functions, the transformation ratios can be written as q I x j. Display style CFRAC partial q caret I partial x underscore j and x I q j. Display style CFRAC partial x underscore I partial q caret j. That is, those ratios are partial derivatives of coordinates belonging to one system with respect to coordinates belonging to the other system, constructing a covariant basis in 3 dimensions. Doing the same for the coordinates in the other 2 dimensions. B1 can be expressed as B1 equals P1 E1 plus P2 E2 plus P3 E3 equals X1 Q1 E1 plus X2 Q1 E2 plus X3 Q1 E3. Display style math BFB underscore 1 equals P caret 1 math BF E underscore 1 plus P caret 2 math BF E underscore 2 plus P caret 3 math BF E underscore 3 equals CFRAC partial x underscore 1 partial q caret 1 math BF E underscore 1 plus CFRAC partial x underscore 2 partial q caret 1 math BF E underscore 2 plus CFRAC partial x underscore 3 partial q caret 1 math BF E underscore 3. Similar equations hold for B2 and B3 so that the standard basis E1, E2, E3 is transformed to a local, ordered and normalized basis B1, B2, B3 by the following system of equations. B1 equals x1 q1 e1 plus x2 q1 e2 plus x3 q1 e3. B2 equals x1 q 2 e 1 plus x 2 q 2 e 2 plus x 3 q 2 e 3 b 3 equals x 1 q 3 e 1 plus x 2 q 3 e 2 plus x 3 q 3 e 3. Display style begin aligned math BFB underscore 1 and equals CFRAC partial x underscore 1 partial q caret 1 math BF e underscore 1 plus CFRAC partial x underscore 2 partial q caret 1 math BF e underscore 2 plus CFRAC partial x underscore 3 partial q caret 1 math BF e underscore 3 math BFB underscore 2 and equals CFRAC partial x underscore 1 partial q caret 2 math BF e underscore 1 plus CFRAC partial x underscore 2 partial q caret 2 math BF e underscore 2 plus CFRAC partial x underscore 3 partial q caret 2 math BF e underscore 3 math BFB underscore 3 and equals CFRAC partial x underscore 1 partial q caret 3 math BF e underscore 1 plus CFRAC partial x underscore 2 partial q caret 3 math BF e underscore 2 plus CFRAC partial x underscore 3 partial q caret 3 math BF e underscore 3 end aligned. By analogous reasoning, one can obtain the inverse transformation from local basis to standard basis. E1 equals Q1 x1 b1 plus Q2 x1 b2 plus Q3 x1 b3 E2 equals Q1 x2 b1 plus q2 x2 b2 plus q3 x2 b3 e3 equals q1 x3 b1 plus q2 x3 b2 plus q3 x3 b3. Display style begin aligned math BF e underscore 1 and equals CFRAC partial q caret 1 partial x underscore 1 math BFB underscore 1 plus CFRAC partial q caret 2 partial x underscore 1 math BFB underscore 2 plus CFRAC partial q caret 3 partial x underscore 1 math BFB underscore 3 math BF e underscore 2 and equals CFRAC partial q caret 1 partial x underscore 2 math BFB underscore 1 plus CFRAC partial q caret 2 partial x underscore 2 math BFB underscore 2 plus CFRAC partial q caret 3 partial x underscore 2 math BFB underscore 3 math BF e underscore 3 and equals CFRAC partial q caret 1 partial x underscore 3 math BFB underscore 1 plus CFRAC partial q caret 2 partial x underscore 3 math BF B underscore 2 plus CFRAC partial q caret 3 partial x underscore 3 math BFB underscore 3 end aligned. Jacobian of the transformation. The above systems of linear equations can be written in matrix form using the Einstein summation convention as x I q k e I equals b k q I x k b I equals e k. Display style CFRAC partial x underscore I partial q caret k math BF e underscore I equals math BF b underscore k. Quad CFRAC partial q caret I partial x underscore k math BF b underscore I equals math BF e underscore k. This coefficient matrix of the linear system is the Jacobian matrix, and its inverse of the transformation. These are the equations that can be used to transform a Cartesian basis into a curvilinear basis, and vice versa, in 3 dimensions. The expanded forms of these matrices are J equals x 1 q 1 x 1 q 2 x 1 q 3 x 2 q 1 x 2 q 2 x 2 q 3 x 3 q 1 x 3 q 2 x 3 q 3 j minus 1 equals q 1 x 1 q 1 x 2 q 1 x 3 q 2 x 1 q 2 x 2 q 2 x 3 q 3 x 1 q 3 x 2 q 3 x 3. Display style math BF J equals begin B matrix CFRAC partial x underscore 1 partial q caret 1 and CFRAC partial x underscore 1 partial q caret 2 and CFRAC partial x underscore 1 partial q caret 3 CFRAC partial x underscore 2 partial q caret 1 and CFRAC partial x underscore 2 partial q caret 2 and CFRAC partial x underscore 2 partial q caret 3 CFRAC partial x underscore 3 partial q caret 1 and CFRAC partial x underscore 3 partial q caret 2 and CFRAC partial x underscore 3 partial q caret 3 end B matrix. Quad math BF J caret minus 1 equals begin B matrix CFRAC partial q caret 1 partial x underscore 1 and CFRAC partial q caret 1 partial x underscore 2 and CFRAC partial q caret 1 partial x underscore 3 CFRAC partial q caret 2 partial x underscore 1 and CFRAC partial q caret 2 partial x underscore 2 and CFRAC partial q caret 2 partial x underscore 3 CFRAC partial q caret 3 partial x underscore 1 and CFRAC partial q caret 3 partial x underscore 2 and CFRAC partial q caret 3 partial x underscore 3 end B matrix. In the inverse transformation second equation system, the unknowns are the curvilinear basis vectors. For any specific location there can only exist one and only one set of basis vectors, else the basis is not well defined at that point. This condition is satisfied if and only if the equation system has a single solution. From linear algebra, A linear equation system has a single solution. Non-trivial. Only if the determinant of its system matrix is non-zero. Det. J minus 1 does not equal 0. Display style det math BF J caret minus 1 NEQ 0, which shows the rationale behind the above requirement concerning the inverse Jacobian determinant. Generalization to n dimensions. The formalism extends to any finite dimension as follows. Consider the real Euclidean n-dimensional space. That is Rn equals R times R times R, n times, where R is the set of real numbers and times denotes the Cartesian product, which is a vector space. The coordinates of this space can be denoted by x equals x1, x2, xn. Since this is a vector, an element of the vector space, it can be written as x equals I equals 1, n, x, I, e, I. Display style math BF x equals sum underscore I equals 1 caret n x underscore I math BF e caret I, where e1 equals 100, 0, e2 equals 010, 0, e3 equals 001, 0, n equals 0001, is the standard basis set of vectors for the space Rn, and I equals 1, 2, n is an index labeling components. Each vector has exactly one component in each dimension, or axis, and they are mutually orthogonal, perpendicular, and normalized, has unit magnitude. More generally, we can define basis vectors by so that they depend on q equals q1, q2, qn, i.e., they change from point to point by equals by q, in which case to define the same point x in terms of this alternative basis, the coordinates with respect to this basis phi also necessarily depend on x also. That is phi equals phi x. Then a vector v in this space, with respect to these alternative coordinates and basis vectors, can be expanded as a linear combination in this basis, which simply means to multiply each basis vector A by a number vi, scalar multiplication. V equals J equals 1, n, v, j, b, j, equals J equals 1, n, v, j, q, b, j, q. Display style math BF v equals sum underscore j equals 1 caret n bar v caret j math BF b underscore j equals sum underscore j equals 1 caret n bar v caret j math BF q math BF b underscore j math BF q. Closing curly bracket. The vector sum that describes V in the new basis is composed of different vectors, although the sum itself remains the same. Transformation of coordinates. From a more general and abstract perspective, a curvilinear coordinate system is simply a coordinate patch on the differentiable manifold n-dimensional Euclidean space, that is diffeomorphic to the Cartesian coordinate patch on the manifold. Note that two diffeomorphic coordinate patches on a differential manifold need not overlap differentiably. With this simple definition of a curvilinear coordinate system, all the results that follow below are simply applications of standard theorems in differential topology. The transformation functions are such that there's a one-to-one relationship between points in the old and new coordinates. That is, those functions are bijections, and fulfill the following requirements within their domains. Vector and tensor algebra in three-dimensional curvilinear coordinates. Note: the Einstein summation convention of summing on repeated indices is used below. Elementary vector and tensor algebra in curvilinear coordinates is used in some of the older scientific literature in mechanics and physics and can be indispensable to understanding work from the early and mid-1900s. For example, the text by Green and Zerner. Some useful relations in the algebra of vectors and second-order tenses in curvilinear coordinates are given in this section. The notation and contents are primarily from Ogden, Nagdi, Simmons, Green and Zerner, Baser and Wycott, and Charlotte. Tenses in curvilinear coordinates. A second-order tensor can be expressed as S equals S I J B I B J equals S I J B I B J equals S I J B I B J equals S I J B I B J. Display style bold symbol S equals S caret I J math BFB underscore I O times math BFB underscore J equals S caret I underscore J math BFB underscore I O times math BFB caret J equals S underscore I caret J math BFB caret I O times math BFB underscore J equals S underscore I J math BFB caret I O times math BFB caret J, where display style script style O times denotes the tensor product. The components Sij are called the contravariant components, Cj the mixed right covariant components, Cj the mixed left covariant components, and Sij the covariant components of the second-order tensor. The components of the second-order tensor are related by S I J equals G I K S K J equals G J K S I K equals G I K G J S K. Display style S caret I J equals G caret ik S underscore K caret J equals G caret J K S caret I underscore K equals G caret ik G caret J L S underscore K L. The metric tensor in orthogonal curvilinear coordinates. At each point, one can construct a small line element dx. So the square of the length of the line element is the scalar product dx and is called the metric of the space, given by dx equals x I q j x I q k d q j d q k. Display style d math BF x c dot d math BF x equals CFRAC partial x underscore I partial q caret j CFRAC partial x underscore I partial q caret k dq caret j dq caret k. The following portion of the above equation x k q I x k q j equals G I j q I q j equals B I B j. Display style CFRAC partial x underscore k partial q caret I CFRAC partial x underscore k partial q caret j equals G underscore I j q caret I q caret j equals math BFB underscore I c dot math BFB underscore j. Is a metric tensor called the fundamental or metric tensor of the Euclidean space in curvilinear coordinates. Indices can be raised and lowered by the metric V I equals G I K V K display style v caret I equals g caret ik v underscore k equals relation to Lamé coefficients equals defining the scale factors high by h I h j equals g I j equals b I b j h I equals g I equals pipe b I pipe equals pipe x q I pipe display style h underscore I h underscore j equals g underscore I j equals math bfb underscore I c dot math bfb underscore j quad right arrow quad h underscore I equals sqrt g underscore e equals left math bfb underscore I right equals left cfrac partial math bf x partial q caret I right gives a relation between the metric tensor and the Lamé coefficients. Note also that g I j equals x q I x q j equals h k I e k h m j e m equals h k I h k j display style g underscore I j equals cfrac partial math bf x partial q caret I c dot cfrac partial math bf x partial q caret j equals left h underscore key math bf e underscore k right c dot left h underscore mj math bf e underscore m right equals h underscore key h underscore kj, where hij are the Lamé coefficients. For an orthogonal basis we also have g equals g 11, g 22, g 33 equals h 1 2 h 2 2 h 3 2 g equals h 1 h 2 h 3 equals j display style g equals g underscore 11 g underscore 22 g underscore 33 equals h underscore 1 caret 2 h underscore 2 caret 2 h underscore 3 caret 2 quad right arrow quad sqrt g equals h underscore 1 h underscore 2 h underscore 3 equals j equals example. Polar coordinates equals, if we consider polar coordinates for R2, note that x, y equals r cos theta, r sin theta, display style x, y equals r cos theta, r sin theta, backslash, backslash, closing curly bracket, r theta are the curvilinear coordinates, and the Jacobian determinant of the transformation r theta, r cos theta, r sin theta, is r. The orthogonal basis vectors are br equals cos theta, sin theta, b theta equals minus sin theta, cos theta. The scale factors are r equals 1 and h theta equals r. The fundamental tensor is g11 equals 1, g22 equals r2. G12 equals G21 equals 0. The alternating tensor, in an orthonormal right-handed basis. The third-order alternating tensor is defined as E equals epsilon I j k e I e j e k. Display style bold symbol math cal e equals var epsilon underscore ijk math bf e caret I o times math bf e caret j o times math bf e caret k In a general curvilinear basis, the same tensor may be expressed as E equals E I J K B I B J B K equals E I J K B I B J B K. Display style bold symbol mathcal E equals mathcal E underscore IJK math BFB caret I O times math BF B caret J O times math BFB caret K equals mathcal E caret IJK math BFB underscore I O times math BFB underscore J O times math BFB underscore K. It can also be shown that E I J K equals 1 J epsilon I J K equals 1 plus G epsilon I J K. Display style mathcal E caret IJK equals CFRAC 1 J var epsilon underscore IJK equals CFRAC 1 plus SQRT G var epsilon underscore IJK. Christoffel symbols. Christoffel symbols of the first kind. B I J equals B I Q J equals gamma I J K B K B I J B K equals gamma I J K. Display style math BFB underscore I J equals frac partial math BFB underscore I partial Q caret J equals gamma underscore IJK math BFB caret K quad right arrow quad math BFB underscore I J C dot math BFB underscore K equals gamma underscore IJK, where the comma denotes a partial derivative. See Ricci calculus. To express gamma IJK in terms of Gij, we note that G I J K equals B I B J K equals B I K B J plus B I B J K equals gamma I K J plus gamma J K I G I K J equals B I B K J equals B I J B K plus B I B K J equals gamma I J K plus gamma K J I G J K I equals B J B K I equals B J I B K plus B J B K I equals gamma J I K plus gamma K I J. Display style begin aligned G underscore I J K and equals math BFB underscore I C dot math BFB underscore J underscore K equals math BFB underscore I K C dot math BFB underscore J plus math BFB underscore I C dot math BFB underscore J. K equals gamma underscore IKJ plus gamma underscore JKIG underscore IK J and equals math BFB underscore I C dot math BFB underscore K underscore J equals math BFB underscore I J C dot math BFB underscore K plus math BFB underscore I C dot math BFB underscore K. j equals gamma underscore ijk plus gamma underscore kjig underscore jk I, and equals math BFB underscore j c dot math BFB underscore k underscore I equals math BFB underscore j I c dot math BFB underscore k plus math BFB underscore j c dot math BFB underscore k I equals gamma underscore jig plus gamma underscore kij end aligned. Since b I j equals b j I gamma I j k equals gamma j I k, display style math BFB underscore I j equals math BFB underscore j I quad right arrow quad gamma underscore ijk equals gamma underscore jik. Using these to rearrange the above relations gives gamma I j k equals 1 2 g I k j plus g j k I minus g I j k equals 1 2 b I b k j plus b j b k I minus b I b j k. Display style gamma underscore ijk equals frac 1 2 g underscore ik j plus g underscore jk I g underscore ij k equals frac 1 2 math BFB underscore I c dot math BFB underscore k underscore j plus math BFB underscore j c dot math BFB underscore k underscore I math BFB underscore I c dot math BFB underscore j underscore k. Closing curly bracket. Christoffel symbols of the second kind. Gamma I j k equals gamma j I k b I q j equals gamma I j k b k. Display style gamma underscore ij caret k equals gamma underscore g caret k. Quad CFRAC partial math BFB underscore I partial q caret j equals gamma underscore ij caret k math BFB underscore k. This implies that gamma I j k equals b I q j b k equals minus b I b k q j. Display style gamma underscore ij caret k equals CFRAC partial math BFB underscore I partial q caret j c dot math BFB caret k equals math BFB underscore I c dot CFRAC partial math BFB caret k partial q caret j. Other relations that follow are b I q j equals minus gamma I j k b k b I equals gamma I j k b k b j b I equals minus gamma j k I b k b j. Display style CFRAC partial math BFB caret I partial q caret j equals gamma caret I underscore jk math BF b caret k. Quad bold symbol nabla math BFB underscore I equals gamma underscore ij caret k math BFB underscore k o times math BFB caret j. quad, bold symbol, nabla, math BFB, caret, I, equals, gamma underscore, JK, caret, I, math BFB, caret, K, O times, math BF, B, caret, J. Vector operations. Vector and tensor calculus in three-dimensional curvilinear coordinates. Note: the Einstein summation convention of summing on repeated indices is used below. Adjustments need to be made in the calculation of line, surface and volume integrals. For simplicity, the following restricts to 3 dimensions in orthogonal curvilinear coordinates. However, the same arguments apply for n-dimensional spaces. When the coordinate system is not orthogonal, there are some additional terms in the expressions. Simmons, in his book on tensor analysis, quotes Albert Einstein saying, "The magic of this theory will hardly fail to impose itself on anybody who has truly understood it. It represents a genuine triumph of the method of absolute differential calculus, founded by Gauss, Riemann, Ricci, and Levi-Civita. Vector and tensor calculus in general curvilinear coordinates is used in tensor analysis on 4-dimensional curvilinear manifolds in general relativity, in the mechanics of curved shells, in examining the invariance properties of Maxwell's equations, which has been of interest in metamaterials and in many other fields. Some useful relations in the calculus of vectors and second-order tenses in curvilinear coordinates are given in this section. The notation and contents are primarily from Ogden, Simmons, Green and Zerner, Baser and Weikert, and Charlotte. Let phi equals phi x be a well-defined scalar field and v equals v x a well-defined vector field, and lambda 1, lambda 2 be parameters of the coordinates. Geometric elements. Integration. Differentiation. The expressions for the gradient, divergence, and Laplacian can be directly extended to n dimensions. However, the curl is only defined in 3D. The vector field π is tangent to the chi-coordinate curve and forms a natural basis at each point on the curve. This basis, as discussed at the beginning of this article, is also called the covariant curvilinear basis. We can also define a reciprocal basis, or contravariant curvilinear basis, by all the algebraic relations between the basis vectors, as discussed in the section on tensor algebra, apply for the natural basis and its reciprocal at each point x. Fictitious forces in general curvilinear coordinates. By definition, if a particle with no forces acting on it has its position expressed in an inertial coordinate system, x1, x2, x3, t, then there it will have no acceleration. d2xj, dt2 equals 0. In this context, a coordinate system can fail to be inertial, either due to non-straight time axis or non-straight space axis, or both. In other words, the basis vectors of the coordinates may vary in time at fixed positions, or they may vary with position at fixed times, or both. When equations of motion are expressed in terms of any non-inertial coordinate system, in this sense, extra terms appear, called Christoffel symbols. Strictly speaking, these terms represent components of the absolute acceleration in classical mechanics, but we may also choose to continue to regard d2xj, dt2 as the acceleration, as if the coordinates were inertial, and treat the extra terms as if they were forces, in which case they are called fictitious forces. The component of any such fictitious force normal to the path of the particle and in the plane of the path's curvature is then called centrifugal force. This more general context makes clear the correspondence between the concepts of centrifugal force in rotating coordinate systems and in stationary curvilinear coordinate systems. Both of these concepts appear frequently in the literature. For a simple example, Consider a particle of mass m moving in a circle of radius r with angular speed w relative to a system of polar coordinates rotating with angular speed w. The radial equation of motion is Mr equals Fr plus Mr W plus W. 2. Thus the centrifugal force is Mr times the square of the absolute rotational speed A equals W plus W of the particle. If we choose a coordinate system rotating at the speed of the particle, then W equals A and W equals 0, in which case the centrifugal force is mA2. Whereas if we choose a stationary coordinate system we have W equals 0 and W equals A, in which case the centrifugal force is again mA2. The reason for this equality of results is that in both cases the basis vectors at the particle's location are changing in time in exactly the same way. Hence these are really just two different ways of describing exactly the same thing. One description being in terms of rotating coordinates and the other being in terms of stationary, curvilinear coordinates, both of which are non-inertial according to the more abstract meaning of the term. When describing general motion, the actual forces acting on a particle are often referred to the instantaneous oscillating circle, tangent to the path of motion. And this circle in the general case is not centered at a fixed location, and so the decomposition into centrifugal and Coriolis components is constantly changing. This is true regardless of whether the motion is described in terms of stationary or rotating coordinates. See also covariance and contravariance. Introduction to the mathematics of general relativity. Orthogonal coordinates. Frenet-Serret formulas. Covariant derivative. Tensor derivative. Continuum mechanics. Curvilinear perspective. Del in cylindrical and spherical coordinates. Further reading. PlanetMath. Org derivation of unit vectors in curvilinear coordinates. MathWorld's page on curvilinear coordinates. Professor R. Brannan's ebook on curvilinear coordinates. Wikiversity. Introduction to Elasticity, Tensors #The divergence of a tensor field. Wikiversity. Introduction to Elasticity, Tensors.